In episode 59, titled Enrichment Strategy, New Sources versus Better Features versus Better Labels, the focus is on improving outcomes by enriching data in the right way, because the fastest path to better performance is often upstream of modeling. When a model underperforms, it is tempting to reach for a new algorithm, but the exam repeatedly tests a more disciplined instinct. Decide whether the limitation is missing signal, poorly shaped signal, or unreliable ground truth. Enrichment is the set of choices you make to change the information available, and those choices can raise the ceiling on what any method can achieve. In real systems, enrichment decisions also involve cost, risk, and governance. So, the best enrichment is the one that improves decision quality without creating new failure modes. If you can reason clearly about sources, features, and labels, you can choose interventions that actually move the needle. Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A useful starting point is to decide whether you need more rows, more columns, or cleaner targets, because those correspond to 3 different kinds of bottlenecks. More rows means more examples, which helps when variance is high, effects are small, rare events are underrepresented, or evaluation is unstable due to limited sample size. More columns means more features, which helps when you are missing key drivers or when the current feature set does not capture the mechanisms that produce the outcome. Cleaner targets means better labels, which helps when the model cannot learn because the target is inconsistent, misclassified, delayed, or defined in a way that does not match the decision you want to support. The exam often frames enrichment indirectly, such as performance is near random, ground truth is uncertain, or important context is not logged, and these clues point you to one of the 3 bottlenecks. When you start by naming which bottleneck you face, you avoid scattering effort across many improvements that do not address the real constraint. New sources are appropriate when key drivers are missing from the dataset, meaning you cannot measure what truly influences the outcome with the data you currently have. In security and operational contexts, this can happen when you only have endpoint logs but not identity context, or you have transaction records but not device fingerprints, or you have outcomes but not exposure metrics that explain opportunity and risk. New sources can bring in missing causal context, such as asset criticality, network position, user privilege, or external threat intelligence, and that context can convert weak proxies into strong predictors. The exam expects you to recognize that if the dataset lacks the variables that drive the outcome, no amount of feature engineering can fully compensate, because you cannot engineer what you do not observe. Adding sources can also reduce confounding by providing baseline variables that make comparisons fairer, which is valuable for both prediction and causal inference. When you narrate the case for new sources, you are essentially saying that the model is blind to important drivers and needs new measurements. Better features are the right investment when the raw fields exist but need structure, meaning the information is present but not expressed in a form that models can use effectively. Raw logs often contain the needed clues, but those clues are spread across events, embedded in strings, or only meaningful when aggregated over time windows. Feature engineering can turn raw events into rates, counts, recency measures, seasonality-aware baselines, or interaction indicators that match how the underlying process works. It can also fix representational issues, such as encoding ordinal information properly, normalizing units, and combining redundant fields into coherent concepts. The exam frequently tests this by describing datasets with rich raw telemetry but weak model performance, where the correct move is to capture structure like frequency, timing, and context rather than to add unrelated new data. Better features should be hypothesis-driven, meaning you engineer what you believe reflects a mechanism, not just more variants of the same idea. When you choose feature enrichment, you are choosing to shape signal into a learnable, stable representation. Better labels are the right investment when target noise blocks learning and evaluation, because a model cannot consistently learn a mapping to an inconsistent target. Label problems show up as weak performance across many model families, strange errors that do not improve with better features, or evaluation metrics that change dramatically when the label definition shifts. In many real systems, labels are produced by processes such as investigations, manual reviews, or rule-based filters, and those processes can vary by team, time period, or workload, creating systematic label bias. The exam cares because improving labels often yields the biggest gain per unit effort when the current target is unreliable, and it also improves trust because stakeholders can understand and defend a model trained on credible ground truth. Better labels can come from clearer definitions, improved adjudication, sampled manual verification, or delayed labeling that waits for outcomes to settle depending on the scenario. When you choose label improvement, you are choosing to make the target a more faithful representation of reality, which increases both learning quality and evaluation validity. New sources come with practical constraints, and the exam expects you to consider cost, licensing, privacy, and timeliness, rather than treating data as a free resource.
Cost includes both acquisition and ongoing maintenance, because integrating a source requires pipeline work, monitoring, and troubleshooting. Licensing and usage rights matter, especially for external data, because a source might be available but not legally usable for your intended purpose or at your intended scale.
Privacy considerations include whether the data contains personal information, how it must be protected, and whether it introduces new compliance requirements, because enrichment can increase regulatory exposure.
Timeliness matters because data that arrives too late may be useless for operational decisions, and delayed features can create leakage if they are only available after the outcome. The exam often tests these considerations by asking what data you should add, and the correct answer is not only about predictive power, but also about feasibility and governance. When you narrate these trade-offs, you show that enrichment is an engineering and risk decision, not just a statistical one.
Domain knowledge is how you prioritize high-impact features first, because it tells you which variables plausibly reflect mechanisms rather than just correlations. Without domain knowledge, you can waste time engineering dozens of features that are easy to compute but weakly connected to the outcome, while missing a small number of features that capture exposure, intent, capability, or constraints. Domain knowledge also helps you choose aggregation windows, thresholds, and interaction structures that reflect real processes, such as account takeover behavior, incident escalation patterns, or seasonal business cycles. The exam rewards domain-based prioritization because it reduces the chance of feature spam, where you add many weak features and increase noise rather than signal. A good enrichment plan starts with features that you can justify in terms of how the system works and how the outcome is produced. When you use domain knowledge well, you are shaping the problem around mechanisms, which leads to more stable and interpretable models. Enrichment can also create risk, so you should avoid adding data that increases leakage risk or compliance burden without clear benefit. Leakage risk increases when you bring in fields that are generated after the outcome, derived from outcome processing, or tied to investigation workflows that only occur once the event is known. Compliance burden increases when data includes sensitive identifiers, cross-domain linking, or retention constraints that complicate governance and audit, especially if the value is marginal. The exam often tests your ability to reject tempting features that predict too well because they leak the target indirectly, and enrichment is a common pathway for that mistake. It is better to choose slightly weaker but valid predictors than to choose invalid predictors that will fail in deployment or violate policy. When you narrate this caution, you are showing maturity. Not all signal is acceptable signal, and not all data is worth the risk. Scenario-based practice is where you decide an enrichment path from constraints and business goals, because the correct enrichment depends on what decision the organization needs to make and what limitations it faces. If the goal is near real-time prioritization, timeliness may rule out sources that arrive days later, pushing you toward features derived from existing real-time logs. If the goal is strategic measurement of program impact, label quality and consistent definitions may be the primary bottleneck, pushing you toward improved adjudication and stable targets. If the scenario implies that key drivers like exposure or privilege are missing, then adding a source that captures those drivers may be the highest impact move, even if it adds integration complexity. The exam expects you to match enrichment to the decision context, because analytics is applied work, not a generic modeling competition. When you practice this reasoning, you become faster at selecting enrichment strategies that change the information landscape rather than tinkering at the edges. Enrichment value must be validated using controlled comparisons against baselines, because adding data can make a model more complex without making it more useful. A controlled comparison means you measure performance and stability before and after enrichment using the same evaluation design, and you confirm that the improvement holds on held-out data rather than only on training. Baselines matter because the question is not whether the enriched model is good, but whether it is better than the best, simpler alternative given cost and risk. You should also look for stability improvements, such as reduced variance across splits or improved consistency across segments, because enrichment that truly adds signal often improves robustness. The exam often probes this by asking how you prove that new data helps, and the correct answer involves evaluation discipline rather than anecdotal success. When you validate enrichment properly, you protect the organization from paying for complexity that does not deliver reliable benefit. Lineage tracking is part of enrichment because enriched data remains valuable only if it is auditable and reproducible over time. Lineage means you can trace where each field came from, how it was transformed, what version of a source was used, and how joins and aggregations were performed. This matters because sources change, schemas evolve, and definitions drift, and without lineage, you cannot confidently reproduce results or diagnose performance changes. The exam treats this as governance and reliability, because decisions based on models must be defensible, and defensibility requires traceability. Lineage also supports operational maintenance, because when something breaks, you can identify which upstream change caused the issue rather than guessing. When you narrate lineage, you are emphasizing that enrichment is not just adding data, it is adding dependencies that must be managed transparently. Communicating enrichment trade-offs is the final piece, because enrichment changes accuracy, complexity, cost, and risk in ways stakeholders must understand to make responsible decisions. Accuracy may improve, but complexity often increases, which can increase maintenance burden and reduce agility. Cost may increase through licensing, storage, and engineering work, and risk may increase through privacy exposure, compliance requirements, and potential leakage. Stakeholders need a clear explanation of what you gain, what you pay, what you risk, and what controls are in place, because enrichment decisions are investments with ongoing obligations. The exam expects you to communicate uncertainty and limits, such as whether the improvement is concentrated in certain segments or whether the added source has coverage gaps. When you communicate trade-offs honestly, you build trust and align expectations, which makes it easier to sustain the model and the data pipeline over time. A useful anchor memory for enrichment is source adds signal, feature shapes signal, labels confirm signal. Sources expand what you can observe, which increases the potential information available. Features transform raw observations into structured representations that models can use, which determines how much of that potential signal becomes learnable. Labels confirm signal by defining the truth you are trying to learn and evaluate against, which determines whether learning can be consistent and whether improvement is measurable. This anchor helps on the exam because it maps directly to the 3 enrichment levers and prevents you from confusing them, such as trying to engineer around missing drivers or tuning around noisy labels. It also helps in practice because it frames enrichment as a system. You need observation, representation, and ground truth to align. When you apply the anchor, you choose the lever that addresses the current bottleneck rather than adding complexity where it does not help. To conclude episode 59, pick one enrichment plan and state your first step, because a plan is only useful when it begins with a concrete action that fits constraints. Suppose the scenario implies that model performance is weak because the dataset lacks exposure and privilege context, so the plan is to add a new internal source that provides asset criticality and user privilege attributes, then engineer time-windowed features that reflect exposure-adjusted behavior. The first step would be to define the required fields and their timeliness relative to the prediction point, ensuring they are available without leakage and that privacy constraints are respected. You would then run a controlled baseline comparison using the existing model and the enriched model under the same time-aware validation design to quantify the incremental value and stability improvement. If the enrichment improves performance and reduces instability, you proceed with lineage tracking and documentation so the new dependency is auditable and maintainable. This is the exam-ready approach. Choose the enrichment lever that addresses the bottleneck. Begin with a feasibility and leakage check, and validate value against baselines before committing to long-term complexity. Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.